Hello good people, I'm going to talk about molecular shapes. In particular, I'm going to demonstrate how the valence shell electron pair repulsion model and the associated electron geometries can be used to determine the shapes of molecules. I'm going to start with diatomic molecules. Recall that diatomic molecules are molecules that consist of only two atoms. Here are four I prepared earlier. I'm going to write out the structural formula for these compounds. In case of hydrogen fluoride, we have H and a single bond F. In case of molecular hydrogen, we have H, a single bond, and another H. In case of molecular oxygen, we have oxygen, double bond, and the second oxygen. And finally, for molecular nitrogen, we have a nitrogen, triple bond, and then the second nitrogen. Although these molecules do not have the same atoms, nor the same bonds, they all have the same molecular shape. In fact, all diatomic molecules have the same molecular shape. They are all linear. To be more precise, and in chemistry we want to be more precise, we would say that they have a linear molecular geometry. Well, that was surprisingly easy. I didn't even use the valence shell electron pair repulsion model. And if all we had are diatomic molecules, we could call it a day here. Unfortunately, most molecules are polyatomic. They are made up of more than just two atoms. Let's look at a few of those. I'm going to get rid of this and bring in three molecules that you should be familiar with. CH4, methane, NH3, ammonia, and H2O, water. I'm going to start by drawing the Lewis dot structures. In case of methane, carbon will be the central atom. Carbon has 4 valence electrons. Each hydrogen brings a valence electron of its own. So let me draw those in. Here are the hydrogens and the associated valence electrons. In case of methane, I have 4 bonding pairs. Here they are, circled in orange. In case of ammonia, the central atom is nitrogen. Nitrogen has 5 valence electrons, and each hydrogen will bring a valence electron of its own. In case of ammonia, I have 3 bonding pairs, circled in orange, and a single non-bonding or lone pair of electrons, circled in purple. In case of water, oxygen is the central atom. Oxygen has 6 valence electrons. Each hydrogen brings a single valence electron of its own, and so we end up with something like this. There are 2 bonding pairs, again circled in orange, but there are also 2 non-bonding pairs of electrons, circled in purple. Although these molecules are quite different, in each case the central atom is surrounded by 4 electron pairs. And this is where the valence shell electron pair repulsion model kicks in. Recall that the electron pairs, regardless of whether they are bonding or non-bonding, are trying to be as far apart from each other as possible. Let me bring in the red sphere and blue sticks. When it comes to the arrangement of the electron pairs around the central atom, all 3 molecules will end up with a tetrahedral electron geometry. In each case, the red sphere represents the central atom. So in case of methane, we have carbon in the center, in case of ammonia, nitrogen, and in case of water, oxygen. What about the electron pairs? In case of methane, all electron pairs are bonding electron pairs, and all 4 bonding pairs serve as a covalent bond between the central carbon and the surrounding hydrogens. In case of ammonia, the situation is different. There are 3 bonding pairs, and each bonding pair connects the nitrogen with a hydrogen atom. However, there is also a pair of non-bonding electrons. When it comes to water, there are two bonding pairs of electrons, and each bonding pair connects the oxygen at the center with one of the hydrogens. However, there are also two non-bonding pairs of electrons. What effect, if any, does all of this have on the molecular geometry? In case of methane, the arrangement of atoms follows the electron geometry, and so this molecule has a tetrahedral molecular geometry. When it comes to ammonia, while the electron geometry is tetrahedral, the atoms of the molecule are arranged in a pyramidal fashion, and so this molecule has a pyramidal molecular geometry. What about water? Again, the electrons are arranged in a tetrahedral fashion. However, the three atoms of the water molecule are arranged in such a fashion to give the molecule a bent geometry. Please note that the electron geometry and molecular geometry are not necessarily the same. The electron geometry will influence the molecular geometry. The electron pairs will arrange themselves to be as far apart from each other as possible. And seeing how electron pairs can be responsible for covalent bonds, the atoms will go where the electron pairs go. While drawing these spheres and sticks is quite fun, it is also time-consuming. So we need a faster way to illustrate the molecular geometry of our molecules. Let's start with water. I'm going to draw the central atom first, that is the oxygen. And now, because I want to illustrate the bent molecular shape, I'm going to draw the covalent bonds at a slight angle. Although it is not always necessary, it is good practice to draw in the lone pair electrons as well. What about ammonia? Well, a similar approach. I'm going to draw in the nitrogen, that is the central atom, and then I'm going to draw in the covalent bonds at a slight angle and trying to convey that pyramidal shape. At the end of each bond, I have a hydrogen atom, and to make this complete, I'm also going to add the lone pair electrons. At the top, we have methane. Carbon is the central atom, and now I'm trying to depict that tetrahedral arrangement. Each bond ends with a hydrogen, so I'm going to add those in as well. And in case of carbon, there are no lone pair electrons. While this depiction of methane is all right, sometimes we want to draw attention to the three-dimensional nature of molecules. Again, I'm going to start with the carbon in the center, and I'm going to draw in the first two bonds as I did before. The next bond will be a wedge, and I'm going to color in that wedge, and the fourth bond will be a dashed wedge. What does all of this mean? The normal lines are in the plane of the paper, or in this case, in the plane of the screen. The dashed wedge points into the screen, while the filled out wedge points out of the screen. We could do a similar thing for ammonia. So here is the nitrogen in the middle. This bond is in the plane of the paper or in the plane of the screen. This bond, as the filled out wedge, is sticking out of the screen, and the bond that I'm drawing as a dashed wedge is sticking into the screen. Let me also add the lone pair of electrons. Alright, let me look at one more molecule, and then you can have a well-deserved cookie. I'm going to get rid of all of this and bring in boron trihydride. Let me draw the Lewis structure for this molecule. I have the boron atom in the middle, and the boron has 3 valence electrons. There are 3 hydrogens, and each hydrogen is bringing its own valence electron. Boron is surrounded by 3 electron pairs, and they are all bonding pairs, so I'm going to circle them in orange. According to the valence shell electron pair repulsion model, these electron pairs will try to be as far apart from each other as possible. So let me bring in the sphere and sticks again. The sphere in the middle is the boron atom. The electron pairs are bonding electron pairs, and they serve as covalent bonds that link hydrogens to the boron in the middle. In terms of the electron pair arrangement, we have a trigonal planar electron geometry. What about the molecular geometry of boron trihydride? Well, once again, the atoms are simply following the electron pairs. There are 3 electron pairs around boron, and all 3 electron pairs are bonding electron pairs. And as the atoms follow the bonding pairs, this molecule will be trigonal planar as well. In summary, the electron geometry and molecular geometry are not necessarily the same. The electron geometry will influence the molecular geometry. The electron pairs try to be as far from each other as possible, and the atoms that make up the molecule will follow those electron pairs. Now that I have made this as clear as a murky tar pit, you can have your cookie. That is all for now, and I will see you on the flip side.